There is a planet 1,100 light years from where you are sitting that has been quietly wrecking one of astronomy's oldest assumptions for over a decade, and most people have never heard its name. It's called WASP-17b, and on paper, it should not exist. It carries less than half the mass of Jupiter, yet it has swollen to nearly twice Jupiter's width, like a beach ball someone forgot to stop inflating. For years, scientists could not fully explain where the extra energy to do that was even coming from. That question still isn't fully closed. And once you understand the actual physics behind it, the clouds on this planet, and the direction it orbits its star, will make a lot more sense and a lot less sense at the same time. First, the setup, because the numbers alone are enough to make you pause. WASP-17b circles its star once every 3.7 days, sitting about 4.9 million miles away, which is roughly 7 times closer than Mercury sits to our Sun. That kind of closeness cooks the day side to nearly 2,700 degrees Fahrenheit. Heat like that isn't the surprising part, though. Extreme closeness to a star always means extreme heat. The surprising part is what that heat appears to be doing to the planet's actual shape. Jupiter, in our own solar system, is dense and compact, exactly what basic physics predicts for a gas giant of its size. WASP-17b breaks that pattern completely. With only about half of Jupiter's mass, it has ballooned out to nearly double the diameter, making it one of the lowest density planets ever confirmed. For a long time, astronomers lumped this under a tidy little label, radius inflation, as if giving it a name meant they understood it. They did not really. Multiple competing theories tried to explain why some hot, close orbiting giants swell up far beyond what basic heat alone should cause. And for years, none of them fully agreed with the data. That unresolved gap matters more than it sounds like it should. Every planet we find like this becomes a test case, a chance to prove one theory right and rule several others out. And WASP-17b, because of exactly how extreme it is, ended up becoming one of the most important test cases in that entire debate. Here's the theory that has pulled ahead of the pack, and it's honestly stranger than most people expect. It's called ohmic dissipation, and the basic idea is this. Planets like WASP-17b are so hot that particles in their upper atmosphere become partially ionized, meaning they carry an electric charge. As ferocious winds drag those charged particles through the planet's own magnetic field, they generate electric currents, similar in principle to a power line, except the power line is planet-sized and made of superheated gas. Those currents don't just fizzle out at the surface. Research modeling suggests they can punch down into the planet's deep interior and dump heat directly into its core, essentially wiring the planet's own weather system into an internal furnace. Now here's the detail almost nobody puts in these videos, the part that turns this from a fun fact into something that actually explains WASP-17b specifically. Studies of this heating mechanism have found it works best on lower mass planets. Heavier gas giants have enough gravity to resist the swelling, even with the extra internal heat, but a lighter planet has far less to push back with. WASP-17b, sitting at under half of Jupiter's mass, while soaking in some of the most intense stellar radiation known, lines up almost perfectly with the exact conditions this mechanism needs to run wild. In other words, this planet isn't randomly puffy. It may be sitting close to the theoretical ceiling of how extreme this effect can get, which is exactly why researchers keep coming back to study it. That single mechanism, an ongoing electrical storm wired straight into a planet's core, was still being pieced together by scientists as recently as the last few years. And it sets up everything else this planet does above the clouds. Speaking of the clouds, this is where the James Webb Space Telescope changed the story entirely. In 2023, astronomers pointed Webb's mid-infrared instrument at WASP-17b through nearly 10 hours of observation during a transit, and they walked away with the first confirmed detection of quartz nanocrystals in any exoplanet atmosphere. Not a similar mineral. Actual silica, the same compound found in beach sand and glass, drifting through alien clouds 1,000 light years from Earth. Here's the part researchers themselves called surprising. They expected magnesium-rich silicates, the kind normally seen in cooler exoplanet atmospheres. Instead, they found something closer to a raw building block, tiny crystal seeds only about 10 nanometers across, smaller than most viruses, forming directly out of gas, without ever passing through a liquid phase. Now, connect that back to what we just covered. High in this atmosphere, pressure drops to roughly 1,000th of what you feel on Earth's surface, but temperatures near the cloud layer still hover close to 1,500 degrees Celsius, and that same superheated, partially ionized gas is the exact fuel driving the ohmic heating happening deeper inside the planet. The glass clouds and the interior furnace are not two separate mysteries. They are two visible symptoms of the same underlying extreme environment, and this environment doesn't sit still. Winds are estimated to move at speeds reaching into the thousands of miles per hour, carrying these microscopic quartz seeds sideways across the planet in a permanent hypersonic storm. You are looking at an atmosphere that is simultaneously generating electricity, growing glass, and hurling both around the planet at speeds that would flatten anything solid. Now for the twist that came before any of this. Back in 2009, when astronomers first noticed WASP-17b was orbiting its star backward, opposite to the direction the star itself spins. At the time, it was one of the earliest confirmed retrograde orbits ever found among exoplanets, and it broke the same quiet assumption Jupiter once represented. Almost every planet we know of, including everything in our own solar system, moves in the same direction its star rotates, a leftover fingerprint from a swirling disk of gas, each system formed inside. WASP-17b doesn't carry that fingerprint. Something disrupted it early on, likely a gravitational fight with another massive planet, or the slow tug of a companion star nearby, either one capable of flipping a young world's orbit over millions of years. Put that alongside everything else we've covered. A planet knocked backward during its formation, then shoved so close to its star that it may sit near the theoretical limit of electromagnetic inflation, now wrapped in hypersonic storms of quartz, grown directly from ionized gas. This isn't three separate strange facts stitched together for a video. It's one planet's entire violent biography, written in its orbit, its interior physics and its clouds, and Webb's ongoing DREAMS program is still actively gathering data to fill in what's missing. So here's a genuine question worth sitting with. If our own solar system's calm, orderly orbits are actually the exception rather than the rule, what does that say about how common WASP-17b's kind of chaos really is out there? I'd love to hear your take on that in the comments, because this is still an open debate among the researchers actively working on it, not a settled answer. WASP-17b isn't a curiosity you file away once the numbers stop being interesting. It's an active physics experiment happening in real time, an electromagnetic furnace wired into a planet's core, growing glass in its clouds, still spinning the wrong way around its star, after everything that knocked it off course. Every telescope observation adds a new page to a story that scientists themselves haven't finished reading yet. And if a world this extreme was hiding in plain sight for years before we understood what we were even looking at, it's worth asking what else out there is waiting for the same kind of second look.